So if a multi-ton industrial transmission fails, the culprit usually isn't like a snapped steel beam.
Right, or a blown motor.
Exactly. It's usually a gap the width of a human hair or maybe a microscopic pocket of oxygen inside a bolt thread.
Yeah, it's the tiny things.
So today, welcome to your custom deep dive. We are zooming way in on the specialized technical deck. It's a guide to precision transmission engineering.
Which is fascinating, by the way.
It really is. Our mission today is to uncover these unseen microscopic design heroes that keep heavy machinery from, literally vibrating itself to pieces.
Because the giant gears,
Yeah.
they might do the highly visible heavy lifting, right?
Yeah.
But it's that meticulous control of the unseen margins that actually dictates whether the machine survives the job.
Yeah. So let's start at the mounting flange. The deck highlights the counterbore, which, on the surface, it just allows socket head cap screws to sit flush.
Right, so the machine's exterior stays completely flat.
Exactly. But in precision transmission, a flush surface isn't like an aesthetic choice, it's a structural necessity.
Oh, absolutely,
Huh.
because when you have these mating surfaces operating under massive torque, any protrusion at all creates an uneven load distribution.
Oh, I see.
Yeah, so the counterbore ensures the clamping force is applied uniformly across the face of the component.
Right.
But, clamping force means absolutely nothing if the initial alignment is even a fraction of a millimeter off.
Which brings us to dowel pins.
Yes, crucial.
The deck really stresses that these hardened steel pins are critical for concentricity, like um, aligning a ring gear housing to a motor adapter.
Right, because you are forcing those components perfectly along the exact same center axis, well before any threaded fasteners are even introduced.
Wait, why before the fasteners?
Because threads inherently have clearance, they have wiggle room.
Oh, right.
If you just bolt two heavy castings together, they will inevitably shift under a dynamic load.
Oh.
So dowel pins take the shear forces entirely off the bolts. They lock in that true geometric center, so the gears mesh perfectly from day one.
Okay, so the dowel pins guarantee perfect alignment when the machine is built. But the second you fire up the motor, you get all this high-frequency harmonic vibration.
Yeah, it's brutal.
So perfect alignment doesn't matter much if the machine just, vibrates its own fasteners loose.
And that is the constant battle in transmission engineering. Mechanical torque inevitably loses to physics when it's subjected to continuous vibration.
So why not just use shear force? Why default to chemistry here? It seems counterintuitive to use a liquid adhesive to hold together high torque machinery instead of just, locking washers.
Well, mechanical washers can still suffer from micromovements, metal fatigue, and just relaxation over time.
Right.
But an anaerobic adhesive, it creates this completely rigid, void-free assembly. And what makes it brilliant is the specific curing mechanism.
Because it stays liquid. Right.
Exactly. It stays completely liquid while exposed to air, which makes assembly relatively easy. But the moment you thread that bolt into the housing, you cut off the oxygen supply.
Wow. And as long as it's in contact with active metal ions, that deprivation of oxygen triggers a chemical chain reaction.
Yeah, it polymerizes into a really tough thermoset plastic. It completely fills those microscopic gaps between the threads.
That's incredible.
It really is. It turns a simple bolt and a tapped hole into basically a unified block of material that just ignores vibration entirely.
Okay, so we've locked the fasteners, but the actual aluminum housing takes a massive beating, too.
Oh, yeah.
The deck goes into detail on hard anodizing to protect those exterior surfaces.
Because, aluminum is lightweight and conducts heat beautifully, but bare aluminum is incredibly soft.
Right, it scratches.
Yeah, it scratches easily and corrodes super fast in harsh industrial environments.
So rather than just painting it, hard anodizing fundamentally alters the surface.
Yeah.
It's an electrochemical process, right, where the aluminum is submerged in an acid electrolyte bath.
Yep, and subjected to high electrical currents. The current forces the surface of the aluminum to rapidly oxidize. You are essentially forcing the metal to grow a ceramic-like armor out of its own base material.
Grow its own armor. That's so cool.
Yeah, and the resulting aluminum oxide layer, it penetrates the substrate and builds outward, giving you this superior surface integrity that honestly rivals hardened steel.
Wow. Okay, so we've chemically locked the frame, electromagnetically armored the exterior, but none of that matters if the internal lubricants leak out or, external contaminants breach the system.
Exactly. Sealing is everything.
And the tolerances on the O-ring grooves in these specs are incredibly tight.
Because you might look at an O-ring groove and just see, a channel milled into the metal. But the precise geometry, the exact width and depth, is arguably one of those critical calculations on the entire blueprint.
Because elastomer seals behave more like highly viscous, incompressible fluids than just solid rubber, right?
Spot on.
Yeah.
Yeah, when you compress an O-ring between two flanges, the rubber actually has to deform to fill the microscopic asperities in the metal. So if the groove is too shallow, the O-ring overcompresses, extrudes right into the clearance gap, and literally shreds itself to pieces under pressure.
Yikes. And if the groove is too deep, there isn't enough squeeze to maintain contact when the system pressure fluctuates, right?
Exactly, which breaks the static seal.
Wow. So the metal groove is essentially a perfectly calculated cage used to manipulate the physical properties of the rubber.
It is. It really reveals the exhaustive, almost paranoid level of control required to keep these macro-scale forces from carrying their own systems apart.
Yeah, I mean, when you step back and look at the whole picture, true precision engineering doesn't actually live in the massive, highly visible moving parts.
No, not at all.
It lives completely in the microscopic margins, the perfectly fleshed counterbores, the chemical certainty of anaerobic polymers, the electrochemically grown armor, and the mathematically flawless compression of an O-ring.
Beautifully said.
Which, leaves us with a wild thought to ponder. We've just explored the extreme measures required to maintain alignment and adhesion at this scale. But as technology pushes aggressively into the realm of nanotechnology, how will future engineers manage these exact same physical forces when the moving parts, the gears, and the seals are literally too small to even be seen with the human eye?
It's a huge challenge.
I mean, how do you lock the threads on a machine built from molecules? Keep wondering about that, and we'll catch you on the next deep dive.